he has become a familiar face. He had an inspiring session on the last day. On behalf of the Department of Mechanical Engineering, Jyoti Engineering College, I welcome you, sir. I remain, you may proceed.
Yeah. So thank you. I think I have taken a session on solar thermal collectors on the first day, second session. So I think you must have got some inputs on how we can use these solar collectors for different applications. So today I'll present on solar solar hybrid systems. So let me share my PPT. Is the PPT visible? Hello?
No, sir.
One second. Yeah, now are you able to see?
Yes, sir. Yes, sir. It is opening.
Yeah.
Dear participants, please mute your mic and video. Yes, sir. It is visible, sir. You can proceed.
Yeah. So good afternoon, everybody. So I think you had an exhaustive session on solar-assisted heat pumps in the morning. So I am going to present on this solar hybrid system. So wherein, along with solar energy, so how we can integrate other type of energy resources. So basically, don't be in a state of mind that hybrid energy systems means only renewable. So we can integrate non-conventional energy sources also into these energy systems. So without much delay, let me go through the presentation. So this is my presentation outline. So I'll be introducing you to this integrated power generation systems. So basically, these hybrid systems are a part of integrated power generation systems. Then I will be focusing on hybrid energy systems, the recent methodologies that various people have adopted in hybrid renewable energy systems. Similarly, how can you evaluate these hybrid energy systems in terms of technical, economic, as well as environmental aspects? Then a few studies which we have conducted at VAT, which include both numerical as well as experimental results. And some more case studies on these hybrid renewable systems, where how can we use this hybrid renewable systems for agricultural application, and some insights on different software tools that are available to conduct studies on hybrid renewable energy systems, as well as challenges and opportunities. Okay. So coming to this integrated energy systems, so these hybrid systems is hybrid renewable energy systems are a part of this integrated power generation system. So wherein these systems are meant for power generation, or you can utilize these systems for solving any energy demand that you require for a different process. So it can be either a domestic process or a commercial industrial application. So that means you can develop these hybrid energy systems from a modular scale, like kilowatt scale to megawatt scale also. Usually, the energy source can be a combination of conventional or non-conventional. So basically, hybrid means you are able to generate either power or energy from two or more resources. So in the case of non-conventional energy sources, energy storage will be an additional component, adding cost to the system. Why? Because basically these non-conventional energy sources like solar, wind, and other things are not reliable. That means they vary with time of the day. So in order to, but your requirement will be constant on the other side. So in order to satisfy your constant energy demand, so basically you have to go for energy storage, which may add some cost to the system. So for your ideas, I have shown one flow chart for this hybrid renewable energy systems. So wherein yeah, so this is the DC bus system. Okay, so on the one side of this DC bus system, you have the energy requirement. On the other side of this DC bus system, you have the generation source. So here you can see that so the energy production is met by solar PV system, and sometimes it is assisted by diesel generator. And as I said, the energy storage. So there can be many types of energy storage, but in this they have shown battery or ultra capacitor. Similarly, fuel cells can also act as a energy developing system. So wherein you need hydrogen and oxygen as an input for basically for polymer electrolyte membrane fuel cells. So where they are using this electrolyzer to split water into hydrogen and oxygen. So those splitted gases are sent into this fuel cell stack. So basically, in this fuel cell, so the chemical energy is converted to electrical energy. So where DC is generated. So, however, in your diesel generator, you get AC power. So again, you invert it into DC, and then you give it to the bus. And on the, as I said, on the load side, either you can have AC loads or DC loads. So since you are giving everything to a DC bus system, so to satisfy this AC load, you need a inverter again, which converts DC to AC. So this SCs are your slave controllers. So wherein this controller will detect which energy generation method to be used when for the specific purpose. And you have a master controller. So where all the energy that is generated from different systems will be going to this, and then this will be directly integrated to your DC bus system to satisfy the loads. So I hope you must have understood what is this hybrid system now. So as I said, these hybrid systems are an integral part of, or one of the classification of integrated power energy systems. So you can broadly classify these integrated power systems as multi-stage systems, cascaded systems, combined systems, and hybrid. So in multi-stage systems, generally these are employed in your conventional thermal power plants, whereas you have multi-stage reheat turbine, multi-stage gas fire, and multi-stage fuel stacks. So basically, these multi-stage systems are employed for high power generation capacities. And in cascaded systems, you have a mercury to steam binary cycle. So basically, cascaded systems are some kind of heat recovery systems. And you have this steam organic Rankine cycle, binary cycle, and a cascaded Breton cycle. Okay. So similarly, in combined systems, you have a combined cycle power plant where you have one output, that is power, and which is meant by different cycles. Then you have integrated gasification combined cycle, that is IGCC, and integrated gasification fuel cell plant. So basically, the power generation happens from gasification as well as fuel cell, both. And in hybrid systems, you have wind and hydro power generation, photovoltaic and fuel cell. So there can be n number of combinations based on how many energy sources you are using. So out of these, hybrid systems can be economical. Okay. And technically, they are somewhat matured and simple in integration. So some of the examples for these hybrid energy systems. So here you can see wind is integrated to solar PV. So we have also done one numerical study on integrating this wind to solar PV and how the energy generation can be improved. So yeah, here you can see that this is for a large scale application where the energy is directly integrated to the state or national grids. So why? Because so currently whatever the wind electric generators that we are getting, so they are in megawatt scale. Okay, and they require some large area so that power generation is possible. Similarly, you have this wind plus compressed air storage system. So on one side you have wind farm, so where it will generate electricity, and on the other side you have the energy generation from compressed air storage. So the main important thing here we have to concern is that so whether the energy generation is same. So whatever the energy that you are producing some wind, and whatever the energy that you are producing some PV, whether both are same. So definitely it will be. It will not be. Okay, so the energy generation depends on various parameters. So similarly here, say you use this compressed air for generation of electricity. And you have this, yeah, as I said, hybrid involves conventional energy sources also. So here you can see that a diesel generator is kept as a backup for energy generation. And you have this wind and solar PV. So wind, usually if you look, so it might be effectively available for 4 to 5 months in a year. However, this solar PV, you can get it if solar radiation available at the location is constant. So similarly, yeah, here you can see that a fuel cell system is also integrated. So as I said, there can be n number of combinations by which you can satisfy your power generation. Similarly, I think Professor Reddy must have told methanol reformation. So here you can see that solar is integrated with this methanol reformer for running this DFMSC. So DM fuel cell system for power generation. So basically here, whatever the energy that you generate will be having low carbon emissions. So basically, hybrid systems are have been pick up more importance because of its low carbon emissions compared to your conventional energy generation. So some of the recent methodologies, this has been taken from a review paper recently published. So some of the methodologies that people are adapting is the hybrid renewable energy sources without hydropower or pumped hydro storage. PHS means pumped hydro storage, and hybrid renewable energy sources with hydropower and pumped hydro storage. So this pumped hydro storage or hydropower depends upon the region. So if you have optimum water resource available, so you can integrate this hybrid renewable energy with hydropower, and you can increase your enhance your power generation capacities. Similarly, coming to the evaluation criteria, as I said, so there are different evaluation criteria like indicators for energy generation, economics, then environmental indicators like that. So what are these indicators? I will let you know in the further slide. Similarly, in sizing methodologies, you have different methods. So there are traditional methods of evaluating the renewable energy systems. Similarly, you have this artificial intelligence method and some hybrid methods. And we have also got some few software tools like Homer, that is hybrid optimization of multiple energy resources. Similarly, have Hoga, hybrid, Transys. This is the effective tool which we have also used for our studies. Okay, so yeah. So coming, I want to give some information on the trend that people are studying on hybrid renewable energy sources. You can see that so India is also contributing much on the hybrid renewable energy sources utilization and studies. So compared to China, so in India, so the articles that are published in recent days are picking up. Why? Because as a nation, we have a lot of renewable energy sources, potential renewable energy sources available in almost all, except a few like geothermal, wave, and tidal. So all other renewable energy systems, we have much potential. So there is lots of scope for installing these hybrid renewable energy sources in future. So that's why many people are studying on how to develop these hybrid renewable sources specific to a location. And similarly, the number of articles published in, so I think this is published in 2019. That's why only some part of publications I have only shown. So, however, in 2019-20 and in some journals, so 2021 articles are also published. So constantly, so you can see that the number of articles published in this area is exponentially increasing. So hence I can say that since a number of combinations are possible, so there is a lot of scope to do research and publish your research. On what topics people are working. So here you can see that many people are working on off-grid applications. Off-grid applications in the sense standalone, where you generate energy and utilize the energy there itself. So one of the advantages with this hybrid renewable energy sources is that you don't depend on the transmission and the distribution network. So especially in remote locations and all, so where this transmission of power lines is not there. So your hybrid renewable energy sources might be a best solution. And few people are working on both on-grid and off-grid applications. And almost 15% of the people are working on grid type applications. And in what journals research has been published, you can see. I think Dr. Mohan Raj also told that he has published articles in renewable and sustainable energy reviews. So most of them are preferring this journal, and some journals like Applied Energy, Renewable Energy are also contributing much in this aspect. On what combinations people are working is, so here you can see most of the people are working on PV, wind, and energy storage. So as I said, PV is available only for during a particular day. Okay, nighttime it is not available. So definitely you have to depend on energy storage. Similarly, wind, as I said, it is available only for 4 to 5 months. So as I said, wind energy generation site require a lot of area. So other than that 5 months, rest of the 7 months, so it will be idle. Okay, so mostly idle. So in the rest of the 7 months, why can't we put this solar PV and enhance the energy generation from the site? So that is what people are working on. Similarly, this is a two source system. Similarly, you have a three source system like PV, wind, diesel, along with energy storage. So almost 15% of the people are working on that. So why I have shown this slide is that so you will have you can get a some idea on in future on what topics I should work. Okay, so some people are working on this PV plus pumped hydro storage, wind pumped hydro storage, and PV wind pumped hydro storage, which is only about 5%. So definitely this can be one of the topics which you can work in future. Similarly, almost 11% of the people around the globe, they are working on hydro plus PV, hydro wind, and hydro PV wind. Okay. Similarly, 17% are the people are working on PV plus energy storage. So as I said, so there is a lot of scope in this PV plus energy storage also. Why? Because in PV you have different technologies like monocrystalline, multicrystalline, thin films, and nowadays we are getting transparent solar cells also. Similarly, in energy storage also we have many topics like battery storage, ultra capacitors, then compressed air storage. So like that, many combinations you can work on, and you can compare these combinations, and then you can publish your papers. So similarly, on the other side, on what evaluation indicators most of the people are working on are reliability of the system and economics. Similarly, 43% of of the researchers are working on conducting the economic studies. So here, one thing you have to understand here is that this hybrid renewable energy sources is a multidisciplinary domain. That means engineers, economics, statisticians, so mathematical people, everybody will be involved in analyzing this hybrid renewable energy sources. Similarly, some environmentalists also will play an important role in analyzing what will be the environmental impact of this hybrid renewable energy sources in future. So like that, so many topics are available to work on this hybrid renewable energy sources. So coming to evaluation, so say suppose that you have pick up a particular combination of hybrid renewable energy source. Either it can be 2-source, 3-source, or a 4-source system. How I should evaluate my combination of system, so that one important thing here is that the more the number of combinations you go, so the cost of the system will increase. Say suppose that if you want to compare between 2 and 3, two hybrid renewable energy sources as well as hybrid renewable sources with 3 resources. So out of these two, energy-wise, economic-wise, as well as environmental-wise, so which one is better? Okay, so to evaluate that, so we have got these reliability indicators. So where you have loss of power supply probability, loss of load probability, expected energy not supplied, then deficiency of power supply probability, loss of load expected, loss of energy expected. So you have to calculate all these things to say that your system is effective. And there are certain formulas available to evaluate this, which I will go one by one. So coming to this loss of power probability, so we can define it in 2 ways. So as shown here. So sigma of a small t equal to 1 to t. So this t represents the time period. Okay. So where d of t is the insufficient energy at time t, time period in kilowatt. And similarly, p load is nothing but the required load at time period t. So basically, the denominator denotes the demand and the numerator denotes the supply. So what will be the loss in power because of the supply to demand ratio. Similarly, you have this sigma of power failure into time. So for how much time the power supplied is less than the energy demand divided by capital T. So where T denotes the total number of time periods. So this gap between the supply and demand, it can be continuous or it can be only for a fraction of time. So if you can sum all the things, then you will get this loss of power supply probability. So these losses may happen, as I said, if you take the case of PV plus wind. Say suppose that some cloudy condition is there maybe for 5 minutes during a day. So that cloudy condition will reduce the power generation from the PV panel. Why? Because as cloud comes, so the radiation intensity will reduce. So because of in solar PV, so the radiation intensity is directly proportional to the power generation. So the more the intensity, the more will be the power generation. So this cloudiness is reducing the intensity of radiation. So thereby the generation from PV will reduce. Okay, so obviously on the demand side, as I said, you need a constant power supply. So either you can meet the reduction in demand either by another hybrid resource, or you can go for storage. Okay. Similarly, loss of load probability. So it is represented by this equation. So this 8760 is the number of hours in a day. That is 365 by 365 into 24. If you take, it will be 8760. So it is the ratio of the power shortage at T hour divided by the load demand at T hour. Okay. Similarly, expected energy not supplied. So it is the sum of the amount of energy that will not be served at time T hour of the year, and E naught is the total energy demand of the system for that particular year. So the ratio of this will give you the expected energy not supplied. Similarly, deficiency of power supply is given by this respective equations. So basically, this DPS, that is deficiency in power supply, is a condition that occurs when the main power generation components or backup units of the hybrid system cannot meet the load demand. So this happens only during certain natural calamities. Okay. So based on the region, if the region which you have chosen is appropriate, so definitely this value will be less. So say suppose in remote locations and all, as I said, you don't have any backup for conventional system, and if you're mandatorily depending on this hybrid renewable energy systems means, so definitely this DPS value will be high. So however, we have to choose the appropriate combination of hybrid systems such that this DPS value is as less as possible. Similarly, you have another indicator, loss of load expected. So where the expected number of hours in a year when the load exceeds the available electricity generation capacity. So this also should be as low as possible, so that you can say that power generation from this hybrid renewable energy sources is very good. And loss of energy expected. So it refers to the expected energy value that has not been supplied. So this is also a kind of difference between the energy required and energy available. So basically, it occurs when the available electric generation cannot meet the hourly load demand. So yeah, it is given by this equation, that is sigma of 1 to H, where H refers to your 24 hours, and into Pi into LEO of I, where it is the LOE of I is the amount of loss of energy when the system could not supply the expected energy at time step H. So another important aspect in this hybrid renewable energy sources is that the reliability of your system. So if you have chosen appropriate necessary components, so definitely the reliability will be good. And another important aspect in this hybrid renewable sources is that whenever you are putting a system, so you have to anticipate the future demand also. Let us say you have developed a system for 100 houses in a locality, and you are expecting that the 100 houses may double in 5 years or 10 years. So corresponding to that, you need to have a sufficient area so that future expansion is also possible. So that is one of the important criteria here. And you have other commonly used indicators like level of autonomy, state of charge, unmet load, and you have respective equations. So I thought that if you go on telling equations, people will get bored. So that's why I'm not going in much detail. And you have some more economic indicators like total annual cost, annualized cost of system, cost of energy life cycle, levelized cost of economy, net present value, like that. And in environmental indicators, we have the carbon emission, embodied energy, then the carbon footprint, then life cycle assessment. So basically, the carbon emissions are the ones which will reveal how much carbon dioxide is released because of the system. And embodied energy is the one. This is also people are considering now. So embodied energy means how much energy is consumed to build that component of the system. Let us say a PV module in a PV array. So how much energy you consume to develop that PV module. So that PV module development will also happen because of use of conventional energy. So let us say one PV module takes around 100 kilowatts of energy to build means. So from conventional energy generation method to produce 100 kilowatt, how much amount of CO2 is released? So that is also considered while analyzing this environmental indicator. And another aspect in this environmental indicator is that so the number of carbon emissions you save, so you can convert it into carbon credits. So you can sell the carbon credits to some conventional energy usage company. So where if they buy that, so they will get some subsidy in the what do you say? So if the company is, let us say, is generating some 10,000 kg of CO2 per year because of the processes and conventional energy usage. So if they buy some carbon credits from this HRES based company, so usually if a company exceeds some limit of CO2, so they have to pay penalty. Okay. So if they are buying this carbon credits, so the penalty they may get subsidized. So usually the thing here is that nowadays this carbon economy is also picking up in developed as well as developing nations. So why that carbon economy has come into picture is that in order to encourage this installation of renewable energy sources, so people are coming with this carbon economy. Similarly, social indicators, so whether any cultural and social aspects are being hampered because of this hybrid renewable energy sources, that also people are looking into, where whether any human development index improvement will be there because of this. In the human development index, in the sense whether any new jobs and increase in technical knowledge of manpower will be increased or not, will come into this human development index. Similarly, job creation, portfolio risk, social acceptance, social cost of carbon. So everything will be coming under social indicators. And you have respective equations to calculate all this. And to make it simplified, so there are some software tools coming up recently, so where all these indicators are included in the software, so that you can analyze the different combinations of renewable energy sources. You can optimize them and pick up the best combination. Yeah, coming to the studies conducted at VIT. So I have done a work with my UG scholars. So where they have come up with a problem statement. So one of the student is from Karnataka. So she had some source to get the data of wind energy site. So what they did is they collected all the data of the site, and they wanted to analyze whether PV can be integrated into the system so that it becomes hybrid, and how much improvement in energy generation is possible. So coming to the wind energy site, it is located at Harpanehalli in Karnataka, and if anybody of the audience is from Karnataka, I think they might know this place. And they have a 36 megawatt capacity wind electric generation site. And in that wind electric generation site, they have observed that the distance between two wind electric generators is about 0.5 kilometers square. So usually we take this 7D and 5D concept to avoid the park effect, so that energy generation is appropriate. So, and that 36 megawatt site has 18 turbines, wherein one turbine is able to generate 2 megawatts. So, yeah, as I said, we wanted to see whether solar PV can be integrated or not. And one of the requirements here is that, as I said, solar PV, you should not have any shade. That means solar PV generation should not hamper because of the shading. So generally, because of the movement of the sun, so the shade of this wind electric generators will fall on the solar PV side. So what we have done is, so we did some site selection analysis for hybrid generation. So we have taken what will be the solar radiation available. So basically for wind electric generation site, so they don't take this solar radiation into consideration. Why? Because they are mainly bothered on how much wind velocities will be available over that site, so that how much energy generation is possible, how much average wind velocities will be available over that location and all. But for solar PV to install, so definitely you require this as the input. Similarly, proximity of the transmission of generated power. So anyway, whatever the power you generate from wind energy, so that they are transmitting it to the state grid. So along with the wind electric generation power, so we can, whatever the energy generated by PV is there, we can directly give it to them. So as I said, one of the primary advantages here is that the rest 7 months of the year where this wind electric generator site is not working, so you can go for PV generation, so that whatever the payback period that is there, you can achieve it very fast. So this work has been published in Environmental Progress and Sustainable Energy. So for identifying this shadow-free region, so we have conducted a MATLAB analysis. Then PV system sizing analysis and balance of systems have been conducted based on the formula available in literature. And we have conducted this technical and economic analysis, both for wind as well as the hybrid systems, and we have arrived at some results. So yeah, as I said, we have calculated the availability of solar radiation. So a monthly average radiation from the site is collected from different sources. Then we also collected what will be the wind resource available at that site. Then as I said, we have done some MATLAB simulation to arrive at what will be the longest shadow and shortest shadow possible at different time period. Okay, so the shadow is based on the angle of incidence of the sun. So as I said, from morning to evening, the sun. So let us say this is east and this is west. So the movement of the sun will be from east to west. So during a certain period of the day, the shadow length will be less, and maybe at noon and all. So the shadow is 0. And as it moves towards evening, so the shadow will be there on both sides of this wind electric generator. So what will be for that particular location, what are the maximum and minimum angle of incidence for 2 different time periods have been studied. And further, what will be the shadow length? So usually this length of the wind electric generator is about 150 meters. So for this 150 meters, what will be the shadow length for 2 different time periods for different seasons have been studied. So we have arrived at 8 o'clock at certain season. So the shadow length is around 550 meters. For the same time, for a different season, it is around 300. Similarly, at 5 p.m., so it is coming to around 5:30 meters, and similarly it is around 280 meters at 5 p.m. So based on this, what we have done is we have drawn circles, shading circles, so to identify the unshaded area. So this is the unshaded area. Okay, so this is on the northern side and this is on the southern side. So as I said, there are 18 turbines. So for each of the turbines, so this shaded circle says that so the shading is possible over this area. So we have used the help of Google Maps to identify the area which is free of shading. So we have analyzed that the shaded free region is about 3,44,531 meters square. And we have chosen a panel of having 1.667 into 1 meter dimension. And based on this, we have calculated how many panels can be kept in this. And there are some equations to find out the spacing, appropriate spacing between the two rows. So we have calculated it to be around 0.61 meters. And since based on the latitude of the location, so we have optimized the inclination to be around 15 degrees from the horizontal. So we have conducted this energy analysis using red screen software. So where we have identified, so based on the number of panels that have been installed in the shaded free region, so what can be the monthly output from that PV array. Similarly, we have also estimated what will be the energy output if you consider 25 years as the life of the PV system. So usually there is a norm that the solar PV panel will degrade with time. Okay, so it will not give you the same amount of power with time. Okay, so what are the assumptions I will show in the next slide. So we have identified that so till 25th year also, so we are able to generate around 35 lakh kilowatts. Okay, so this much amount of energy is possible within this area. So if you take that 25th year also, you can generate up to this. So as I said, what are the assumptions we have taken? So we have considered the values based on CREDL, that is Karnataka Renewable Energy Development Energy Limited. So they have specified the cost. Per megawatt, it is assumed that 10 crores will be the initial investment cost. And operation maintenance cost will be about 10 lakh per megawatt per year. Okay. So this, as I said, per year, so for 25 years, we have assumed it to be around 2,500 lakhs per year per megawatt, and we are generating around 36 megawatts. So correspondingly, the value will change. And coming to the tariff, so if you generate 1 kilowatt, so what will be the selling price? So according to this CREDL itself, so we have assumed the selling price to be 5 rupees. So they mentioned it can be anywhere between 4.69 to 5.5. So and we have taken an average value of 5 for this study. And as I said, energy degradation. So we assumed that 4% loss of power will be there for first year, and the corresponding respective years. So there will be a degradation of 1.5% compounded each year. So for this investment of 10 crore per megawatt, so we have calculated what will be the payback. So we have done some cost analysis and arrived at this number. So within 9 years, you can get your payback. So if you assume that your life of the system is 25 years, so the after 9 years, whatever the amount that you are getting is all profits. So for the rest 16 years, so after this 9th year, so whatever the till the life of the solar PV system. So for the next 16 years, so you can get much profits. So for conducting this particular analysis, as I said, we have used red screen, PVSys, and MATLAB softwares. And so this is for PV system. If you take the break-even period for both, considering both wind and PV system, so the investment that you made, you can get within 6 years. So I hope for wind electric generators also, the life of that wind electric generation system is more than 20 years. So if you assume it to be 20 years also, so for rest 14 years, whatever the power that is generated, it will be all profits. Yeah, so based on that cradle assumptions, so for this wind plus PV hybrid system, so 188 crores will be the investment cost. So we have mentioned it in US dollars also. Why? Because that particular publisher wanted the cost to be mentioned in US dollars also. That's why we have mentioned here. Considering one US dollar to be 69.85 during that time. So annual maintenance cost, everything. So the net present value has been arrived at around 240 crores. So based on this initial rate of return and benefit to cost ratio and other things. So the net saleable annual energy production is coming to around 98.16 million kilowatt hours. Combining both wind plus PV. So earlier with only wind, so we are not getting this much power. So we have calculated that the energy generation rate has been increased by 54%. So it's almost more than double. Okay. Yeah. So these are the conclusions from that particular thing. So we can say that this much amount of energy you can produce with this wind hybrid system, and yeah, so solar is able to give this much. So combining both the solar plus wind, so we are able to get 9 crore 81 lakh 60,000 kilowatt hours. So as I said, so the power generation capacity has increased by 54%. So we have given this, presented this analysis to the company which is maintaining the site. So they also got impressed, and they said that we will definitely try to implement this in that site so that their payback can be reduced. As I said, we have done only a simple break-even analysis and arrived at this 9 years as the break-even period. Yeah. So the net present value. This is a one type of cost analysis. So it resulted in around 1,040 as the present value. That means at present. So if you invest 980, so the present value will be increased to 1,040 crores. Yeah, coming to another important and interesting study. So we have made a generation plant. So this is a part of DST project done along with my colleagues. So what exactly is this tri-generation is? So we can get three types of output. Okay, one is power, the other one is cold air, and potable water. So yeah, here you can see how the system is. So here you can see that why I said it is a hybrid means, so you're one side you are using solar water heater, and you're using this this concentrated system also, and yeah, you have many heat exchangers and other things available. So whatever these numbers that are there, so they represent the state points. Okay, state points in the respective system. So yeah, I will show you one video so that you can understand that better. So here you can see that it starts from 1. Okay, so we have taken a screw compressor for this study. So first state point is this place where ambient air is sent into this compressor, and the high pressure air is sent into this receiver where we have considered a Scheffler concentrating collector for this analysis. So here the temperature and the pressure of air will be increased, and it is further sent into this biomass combustion. This is a gasifier. It's not exactly a gasifier. It is only a heat exchanger which adds up temperature to the outcoming air that is coming from this receiver, and from there it is going into this air turbine. So this air turbine capacity is about 4 kilowatts. So here for this compressor, we are giving an input of around 3 kilowatt, and at the air turbine, we are able to generate 4 kilowatt. That means there is a positive energy that we can generate from this system. So that means whatever the 4 kilowatts energy that is generated, so in that 3 kilowatts is given to this compressor, and 1 kilowatt you can transmit. So why this air turbine power generation is less means, so we have customized this product. So we have not taken any commercial thing. So basically, if you can improve this air turbine efficiency, so definitely the because since we have fabricated using local available resources, so we are not able to get much efficiency. So if you are able to build up this air turbine with some precise things, so definitely we have done some calculations, and we have arrived at that the power generation can be improved up to 5 kilowatts also. That means 3 kilowatt if it is going for compressor. So 2 kilowatts will be the positive side of energy generation. So, yeah, so from air will be going into this combustion to increase the temperature. So further it goes into this air turbine where power generation happens. So after power generation, so this is again going into this heat recovery heat exchanger. So where heat will be given to this. This is a vapor absorption machine. So basically, for this vapor absorption, you need heat as a source. So that heat is given from this rejected air that is coming from this air turbine. So here we are generating power, and at this vapor absorption system, we are generating cold air. Okay, so we have two outputs here. So further, we have used this heat for many using many heat exchangers. We have used this heat to be required in many places. So you can see that there is 1 to 62 state points. Okay, that means you have taken air, water, and refrigerant as the three working fluids. So air is generating power here, and this refrigerant is generating the cooling. It's generating the cold air, and you have this chilled water where you can use it for getting the potable water. So yeah, here 1, 2, 3, 4, 6. Yeah, so this after exchanging this heat to this vapor absorption machine, So again, it is sent into this air preheater, where this air preheater is also a kind of heat exchanger. So the heat source for this air preheater is getting from this solar flat plate collectors or solar air heaters. So heat source from this is going into this. And why we have considered air preheater here is that so since the heat is exchanged here, so the temperature will drop. So to further enhance this temperature of air, we have used this low cost solar air heater to give heat to the air. So another aspect of increasing the temperature of air here is that so to increase its saturation level. So here the air is sent in, this is a two-stage humidifying process. So in the first stage, so the heated air goes into this humidifier, and cold water is sprayed from the top. So what happens is that this hot air, since its relative humidity will be less, so it will absorb the moisture that is falling from this cold water, and again it will go into this dehumidifier. So in this dehumidifier, so it is also a kind of heat exchanger where inside the tubes, chilled water. Here, chilled water in the sense it is normal water that is available in the overhead tank. So since this air is at a very high temperature, so there will be large difference between the delta T of water to air. So that delta T is enough to cool down or condense the water vapor that is available in the air. And once the condensation happens, so that condensed water is collected at the bottom. So here the inlet cold water temperature will be somewhere about 25 degrees or so. So once it exchanges heat, so the temperature of water increases to around 10 degrees because of exchanging heat with this air. So so this is one place where we can collect the condensed water, and again the same air is sent to the second preheater. For the second preheater also, the source is the same air that is coming from this solar flat plate collectors. So the air is heated and it is given as input to the second humidifier. So here the humidification process is not 100%. So some more moisture is present in this air, so that is retained or collected in the second humidifier. So before it is going into this dehumidifier, so there is a great heat exchanger that we have given, so to improve its saturation levels. So again, chilled water that is coming from cold air that is coming from this VAM machine, vapor absorption machine, is given as input to the second humidifier, so that the moisture that is available in the air is completely get condensed, and it will be collected at the second humidifier. And so this chilled water, whatever is coming from this VAM machine, will be somewhere about 5 degrees, which based on calculations which we have done. So since it is cooling down this air that is coming from this second humidifier, so the chilled water temperature will rise to around 13 or 14 degrees. So for our AC applications, so 13 or 14 degrees is enough to cool the space. So we don't need a very chilled air, which is at 5 degrees or so. So in order to increase its temperature, so it will take the heat from this second dehumidifier, and the temperature is increased to around 14 or 15 degrees, and that air is sent into this AC load for cooling applications. So that means in first attempt itself, you may not be able to understand this. However, so here we have generated power, and we have generated refrigeration thing, and we have obtained this condensed potable water. So the system which we have designed, we are able to get around 12 liters per day. Okay, with two dehumidification process. With one first stage, we are able to get only 5 liters. So in the second stage, we are able to get 7 liters. Why? Because the temperature of chilled water is somewhat more compared to the normal water that we are getting from the overhead tanks. Okay, so the delta T available is more, so that's why the more condensation is happening at the second humidifier. So I am not able to present all the results. Why? Because we are yet to publish. So this work has been conducted 2 years back, but still we are able to publish much papers. Why? Because there is a lot of data available with us. So slowly we are publishing, adding some more analysis to that. So in conclusion, we can say that we are able to increase the energy utilization factor of the whole system from 0.182 to 0.333 based on the numerical studies which we have conducted, and we are able to optimize this vapor absorption refrigeration process for maximizing the energy utilization factor. So the lower limit of separated temperature, we are able to get around 100%. And there is a deflect meter here in this diagram at 49. So what is its feature is that, so as I think some of you might know that usually in vapor absorption machine we will use ammonia water or lithium bromide water as the refrigerant. So the defect, whenever you give heat source for this VAM machine, so basically the ammonia or lithium bromide, which is having low boiling point temperature, will evaporate. So during this evaporation process, along with ammonia, so some water may also get evaporated because of the surface evaporation. So that will go into this deflect meter, and here again the water will be getting separated from ammonia, and only concentrated ammonia will go into this evaporator section. Okay, so that's why this deflect meter is kept here. So effectiveness of this. So deflect meter, don't think that it is something sophisticated. It is also a kind of heat exchanger only. So we are able to increase that heat exchanger effectiveness to around 0.65, and the lower possible circulating water temperature we are able to attain at 30 degrees, and the evaporator temperature we are able to achieve at 10 degrees. And so this is very important. A strong solution concentration of 0.47 is obtained. So if you look into the literature, nobody has attained concentration of this level. Yeah, so nearly, as I said, based on calculations, so 1.5 liters per hour of fresh water and about 175 watts of cooling load we are able to generate. And one more thing here is that understand that so this whole process happened, that means this has been operated from 10 to 3 p.m. Why? Because before 10 and after 3, so we may not be able to get much intensity of solar radiation such that this receiver at this exit of receiver you will get higher temperature of airs. So usually ambient conditions itself, the temperature of ambient will be low, and the amount of concentration that we obtain before 10 and after 3 is very, very less. So that's why this system will work effectively during 10 to 3 p.m. Yeah, so it is observed that from conventional single stage humidification and dehumidification plant. So the desalination yield not resulting at very low temperatures. So we are able to increase that energy utilization factor from 0 to 3.5, that is using two-stage dehumidification process. So, and hot water we are able to get around 150 to 200 lph, which we have obtained from the air turbine. So these are the few publications that we have published. So coming to the next case study, I think, so how much time still I have? I can go up to 110, is it okay?
Yes, sir.
Okay, okay. So the second case study, so this has been done by one of my collaborators. So along with two other institutes. So one is in Bhopal and another one is in Anand, Gujarat. So he was earlier working with this SPERI, that is Sardar Patel Renewable Energy Research Institute. So along with these two institutes, they have developed this technology. So as I said, this is for a agricultural application. So the title of this study is Development of Solar Hybrid Refrigeration Technology for on-farm safe transport storage of horticultural produce. So where they have taken the help of solar PV, some energy storage in terms of battery, so which are used to operate this cold storage unit. So usually in the conventional process, you can directly run this VCR with this solar PV. However, in VCR, I think Dr. Mohan Raj also mentioned that currently many refrigerants which are having high global warming potential are also used. So, what is sorry. What is the idea here is we have to replace this VCR with vapor absorption machine. But for that vapor absorption machine, you need a heat source. So for that, what they have done is, so they have taken the help of solar evacuated tube collectors. So this is the overall plant layout that is established in Bhopal. So they have installed a 25 kilowatt solar photovoltaic system, and this is the steady area where a cold storage room with vapor compression system has been established. So they wanted to analyze what will be the economic as well as environmental and energy aspects comparing two different combination of hybrid sources. So one combination was with solar PV and vapor compression system, and another combination is with solar PV, solar flathead collector, which gives thermal energy plus vapor absorption machine. So along with some energy storage. So these are the real-time photographs. So the energy output that they have estimated is about 80 to 110 kilowatt. That is 80 to 110 units per day. So on an average for different months of the year. Yeah, this is a cold storage unit. So inside this cold storage unit, they kept the agricultural produce and studied the characteristics of that horticultural produce. So especially in Gujarat and all, if you see, so they are food manufacturers of. That means there you can see large varieties of mangoes to be produced. So those mango storage and all they did, as well as they did for tomato and other products also. So for this, they have considered this 2.5 ton of refrigeration of vapor compression system. So the requirement is that the unit should be maintained at 2 degrees with a relative humidity of 95%. And the capacity of this unit is it can store up to 6 to 8 ton of horticultural produce. So yeah, in the earlier case, I told we have used ammonia water system. So this is a LIBR system. So the advantage for going for LIBR is that this lithium bromide is not that harmful. However, your ammonia is carcinogenic. So that is one of the challenges that we have also faced. So if you want to develop this ammonia-based system, so it should be leak-proof. If a small amount of ammonia is leaking, so it will directly affect our lungs. So we have to be very, very careful with ammonia. So, so compared to ammonia, this LIBR is much better. But in this, one of the challenges is that you have to have a maintain vacuum. Okay, so vacuum means not 100% vacuum. So vacuum up to 20% of vacuum should be maintained for operation. And these are the corresponding operating parameters. And the generator, the inlet temperature of water to be at 88 degrees. And after this heat exchange, so the outlet temperature was 80 degrees. That means there is a 8 degree drop in the hot water temperature. And at the cooling water inlet temperature, so this may be closer to your ambient, so which is about 32 degrees. And at the evaporator, you get chilled water inlet temperature to be 9 degrees and outlet, so there will be a 3 degree drop, that is 6 degrees. And at the absorber, the cooling water outlet temperature is about 36 degrees. I think most of you are familiar with this vapor compression system. So this vapor absorption system is also similar. Instead of a compressor, you have a generator here, where this LIBR will be the working fluid. So once you give heat to this generator, so this lower boiling point fluid, whatever is there, so that will evaporate first. So yeah, so this LIBR will evaporate and it will go, and the remaining dilute fluid, whatever is there, that will come to the absorber. So once this LIBR goes here at the condenser, it will condense. Then you have a throttle valve, and then finally the evaporator, where the heat is taken up. So that means the condensed liquid will evaporate, and then the vapor will again come here at the absorber. Both will mix, and the concentrated mixture is again pumped into the generator. So this is the principle of working. Yeah, coming to this LIBR based theoretical effectiveness. So theoretically, our ideal efficiency is 1.004. Okay, for this operating conditions. However, theoretical COP for the conditions available at that location, so they are able to get around 0.7, which is somewhat closer to the ideal COP. So, so all this COP you can increase based on the conditions that you maintain. This is a cross-sectional view of the WAM machine that they have developed. So on the top you have condenser, generator, evaporator, and absorber. So this is the WAM machine that they have manufactured. So they have manufactured this with the help of Tata Industries. So these are the readings that they have taken under full load and part load. So for full load and part load, they have calculated what is the resulted COP. So here you can see that at full load conditions, so the COP is in the range of 0.6 to 0.7. Which is closer to their critical COP. So as I said, this COP will change based on the operating parameters that you consider. And full load means if the cold storage unit is completely occupied. Part load means at a different volume loads they have taken, and there also they observed that the COP is ranging in between 0.57 to 0.64. So there is not much drop in COP because of full load and part load conditions. Yeah, these are the different operating conditions that they maintain in the chamber. And as I said, yeah, so in order to replace that vapor compression system, so a vapor absorption machine is installed. So for that, heat is the input. So either you can get that heat put from solar collector array. Say suppose that because of rain and other reasons, say suppose we are not able to generate hot water from that. So you can use a biogas plant wherein that if you burn that biomass, so that heat will be released. That heat you can utilize to generate hot water. So that hot water you can give it to the VAM machine for operation. Okay, so whatever the output from this VAM machine is, then you can directly connect it to the cold rooms. So basically, chilled water is circulated in this cold rooms to maintain the appropriate temperature in the cold room. So these are the actual photographs taken at the site. So this is the vapor absorption machine which I was referring to. So this is a 5-ton capacity. So earlier in the VCR it was only 2.5 ton, but usually since the COP is less compared to your compression refrigeration, so obviously the size of the vapor absorption machine will increase. So these are the fluid circuits for chilled water and hot water. This is a hot water tank which is maintained at 80 to 90 degrees centigrade. So chilled water tanks before going into the cold storage. So this is the whole system. Okay. So this is the thermal collector field from where hot water is generated. Yeah, coming to this thermal efficiency aspects, so for different input conditions, you can see that the efficiency is ranging from 0.36 to 0.46. So, and one more important thing here is that, as I said, the input solar energy is not constant throughout the day. So the output temperature in the system will vary. Correspondingly, the thermal efficiencies and flow rates will change. Okay, so here in this table, they have shown it for lowest radiation to highest radiation. So, and here, I think if the solar radiation is doubled, so the change in thermal efficiency is only 0.1, sorry, 10% change. Okay, it is not much. Yeah, these are some of the results. Anyway, I will share this PPT. You can just go through. Yeah, coming to this COP, so for different operating conditions, you can see that this is under full load conditions. It is ranging in between 0.58 to SAM1. This is the power plant, solar PV power plant. As I said, they have used tomatoes and mangoes to analyze how the food characteristics will change. This is the actual storage condition. So they have installed the mangoes in the cold storage. Yeah, so with the time, you can see how the cold storage temperature changes. So they have installed 4 temperature thermocouples at 4 places in the cold storage. And for different time, so they have seen how the variation in temperature is there. So initially, almost all the thermocouples showed the same reading. So after 75 minutes, so that means it took 75 minutes to come to this temperature. Actual requirement is 2 degrees. So it will take some time to get this 2 degrees temperature. Coming to the shelf life, so without keeping it in cold storage and with keeping it in cold storage and at room temperature, you can see how the shelf life changes. So for different mango varieties, they have analyzed. So almost all the varieties showed better shelf life when they are kept in cold storage. However, this Totapuri has the highest shelf life when it is kept at room temperature of 7 days. Others, they were only fresh till 6th day. So after that, its quality is getting spoiled. But with cold storage, you can see that. So they have. When I discussed with him, he told that if appropriate, so usually this should not when you are keeping in cold storage, you have to make sure that so the products should get shuffled. Okay, so you cannot keep it constant. So if you are able to shuffle, I think the maximum they are able to get up to 45 days also. Okay, so shelf life they are able to increase gradually. Coming to the different software tools, as I said, they have traditional methods, artificial intelligence methods, and hybrid methods. So each of these methods have their advantages and disadvantages. In the traditional methods, we have a graphic construction method, which uses basic analysis. Probabilistic methods are there, which are also simple, but you cannot use it for optimizing the hybrid systems. And you have iterative method, as name iterative is there. So there will be a loop process for optimization. And people have identified that they are better than commercial softwares like Homer and genetic algorithm based softwares. And numerical methods, you have deterministic and stochastic methods. So according to whatever input you take, so correspondingly the output delivered by that method will change. And in analytical method, you have different computational models. So based on the degree of equations that you take, so the output will vary. And in artificial intelligence, so mostly it is run by MATLAB codes. You have genetic algorithm, particle swarm methods. So I think some of you must have listened to these words: simulated annealing, ant colony optimization, artificial bee colony, harmony search, cuckoo search, like that. Many different codes are available, so you can use them respectively to arrive at the feasibility analysis of hybrid systems. And in hybrid methods, so these are extension of your MATLAB codes. So I think there are only few are listed here. There are many methods available further, and this is very important. So we can use both open source as well as commercial softwares to arrive at. So those who are students, so you can effectively use this open source softwares to understand the energy generation from hybrid sources. You have Photourgel, Osmosis, NEMS, Energy Plan, BHP, Compose, like that. Many open source softwares are available, so you can use it to understand that. And in commercial softwares, we have Homer, that is hybrid optimization of multiple energy resources, and HOGA, hybrid optimization by genetic algorithm. You have hybrid, two hybrids, PV system, PV solar also you can use to optimize your solar PV installations. Yeah, coming to the challenges, so establishing an hybrid renewable energy system is not that easy. Okay, so some of the challenges are listed here. So these are only few, not complete. So basically, the reliability of energy generation is different. So if you say an example of wind plus PV, as I said, so based on the wind speed and wind direction and all, so the amount of energy generation from wind will change. And correspondingly with solar PV also, if the radiation, temperature and other things change, so the energy generation capacity may change. So we may not have a common energy output from both the sources. Then reliability of data for simulation and pre-feasibility analysis. So say suppose that if you want to establish that at a particular location, so you need to get all the data for simulation for that location. So obtaining the data is somewhat difficult unless only for certain regions it is available. So for other regions, you have to pay money and get the meteorological data to perform the pre-feasibility analysis. So unless you conduct the pre-feasibility analysis, you cannot say that the site is suitable. Then, so government policies as well as local body policies should change to encourage this hybrid sources so that carbon footprint can be reduced. So slowly it is picking up. So the pace should somewhat increase so that the carbon footprint on the earth is reduced. Then availability of technical manpower. So we need to conduct more and more training programs for the existing staff so that everybody will get knowledge on how to operate and maintain the hybrid renewable energy systems. Because conventional generation is somewhat different from hybrid systems. Then the end users who are there, they also should encourage these hybrid systems. Then, as I said, cost and components. So there are some maintenance issues. Say, suppose if they are established in remote locations, so service network and other things will be a problem. And regarding the cost, some new materials development should happen so that it can be made more economical. And there are more challenges in energy storage. As I said, it is reliable. So obviously you depend on energy storage for constant power supply. So there should be some more insight to be given for energy storage technologies. Thank you for your patient listening. I think it's 1:05. So if you have any questions.
Thank you, sir. Thank you. The participants can ask the questions now.
Are there any questions in the chat?
No, sir. Earlier there was one question. So which software you used for that simulation? Then I asked them to ask at the end. Participants, can you please ask your questions?
I think I have mentioned.
Doubts?
I have mentioned in the PPT, right? Red screen, PVSys as well as MATLAB simulation for my UG students' work. Some information on solar panel car or in automobile industry. So can this question be specific? I'm not able to get the question. Dattaguru Savarkar. Solar cars.
Hello.
Yeah, yes. Samiran, yes.
Hello, sir. Good afternoon, sir.
Yeah, good
Yes,
afternoon.
sir. Sir, I am from I am from KT University, Bhubaneswar.
Yeah.
Sir, is that simulation has been done on Transit software? Because it seems like that it has been done in Transit.
We have tried, but we have shifted
Yes.
to red screen. Transit also it is possible.
Which software?
Transit also it is possible, but we have used red screen.
Yes, sir. RAT screen.
Yeah, RET screen, yes.
RAT screen. So, sir, is it a open source software or freely available, or we have to buy it?
No, there is open source as well as commercial available, but the features you get in open source is somewhat limited to commercial ones. So the capacity
Okay, so,
of computation is less in open source. That means in there is a trial version, not open source. There are trial versions. If you want to get commercial ones, we have to pay money. So obviously the features will also be more. Yes.
Okay, so sir, whatever that complex circuit you have shown there, so it was fully done in RAT screen.
No, some part. The economics part has been done in red screen. The PV simulation part we have done in PV-Syst. So that PV-Syst is available in our institute. So we have used that to get the energy generation from PV. And wind energy data, the company has provided. So the company which is maintaining that wind energy site, so they have provided us with the annual power production figures. So based on that, we are able to couple both PV plus wind energy. Yes.
Okay, so after some results you have generated in PV-Syst and some results has been generated in RAT
economic analysis. Economic analysis, we have taken the help of RET screen. And the
so,
shadow analysis.
Sir, you have mentioned that something about MATLAB. So, can we use that MATLAB or engineering equation solver?
No, that's what. MATLAB completely you cannot do. MATLAB we have used for getting the shadow analysis. There are some other commercial softwares available to understand the solar optics since they are costly, and our students they are quite happy to do the MATLAB coding. So they have taken the equations available in literature, and they have adapted that equations to that location and arrived at what will be the shadow ranges and other things. Yes.
Okay. So that means in one single software it is not possible. So we have to amalgamate.
No, it's not. I am not saying that it is not possible, but you have to pay some money. So since they are students, they are students. They are not able to get that, and you know that UG projects are limited time. So most of the things they have completed with trial versions only. Yes.
Okay.
No,
Thank you,
no.
sir.
Why I have shown that is that you can get some simple solutions for improving the energy generation.
Yes, sir.
That's what. So,
yes, sir. Yeah. Actually, sir,
those who are students, those who are students, they can get some motivation on the methodology that they can adopt. Yes,
sir. Yeah. Sir, actually, sir, we have also started here, and some of my students also have started working here. So one kind request from my side. So if you will not, if there will not be any problem, so can you share this lecture either in the PDF format or something else for our self study?
I will share that with the organizers. So I think they can get you with that. So definitely.
It's my sincere.
Sure.
Request.
Sure.
Actually, sir, I am attending many short-term courses, but actually the speakers are not very much likely to share their.
Anyway, you know my name.
Sir, we have few more questions in queue.
Right?
Okay, sir. Okay.
So anyway, you know my name and institute, so you can send me a mail. I will definitely share it.
Sure, sir. Thank you, sir. Thank you.
Yeah, Deepan, sir.
We have a few more questions, sir. Hybrid system on a small scale. Will it be economically feasible?
That depends upon what sources you choose. Okay, so if you take solar PV, so if you consider the cost of solar PV system maybe a decade back, so the cost has been constantly reduced. So I think I can say that by 7 to 8 times the cost of solar PV has reduced. So definitely solar PV can be one of the hybrid sources. So you can appropriately choose another source which is specific to that region. So if you feel that solar energy is ambient, actively available, so you can use solar energy. Or if wind energy is the source which I can take, means you can take wind energy. I think wind electric generators are also available in modular scale, especially in this vertical axis wind turbines and all. If you want to do it for one domestic application, so definitely you can integrate both solar PV plus vertical axis wind electric generator. If I am correct, vertical axis wind electric generator 1 kilowatt, I think it will cost around anywhere between 10 to 15,000 based on the company. So if you want to have 3 kilowatt system at your house means, so 2 kilowatts you can go for solar PV. I think it costs about 1 lakh. And 1 kilowatt, if your region is more prone to wind, so definitely vertical axis wind turbines can be one of the best options. So it all depends upon, that's what you have to do some pre-feasibility analysis before choosing the appropriate choice of combination. For PhD scholar, which simulation is suitable for SAH? What is this SAH? Dasari Nalini. I am not able to get the abbreviation.
That may be solar hair heaters.
Solar air heaters. So I think Transys simulation is a better tool, but Transys is not free. Okay, you have to purchase. I think they are giving in modules also. Transys, they are able to provide the software in modules. So if you want a specific module, maybe solar air heater means you can purchase, no problem. Because Transys, what is the advantage is that so the meteorological data you can since the database of Transys is connected with different meteorological databases, so no need to purchase the meteorological database separately. Okay, so within that simulation, if you put the latitude and longitude, so the corresponding meteorological data, the simulation software itself will assume. Next question, is it necessary to produce continuous heating and cooling effects like electricity? If so, could you mention some applications? Samuel, I am not able to get your question. Is it necessary to produce? For which application you are telling? Is it for refrigeration? Samuel? So I hope I must have answered Dasari Nalini's question. If it is solar air heater. If she is asking for open source softwares, I think there are there. Since I didn't use it, I don't have any information on that. But simulation of solar air heater in open source software, I think it is possible. Yeah, any others? Samuel is there. Yeah, Samuel.
Yeah.
Yes, Samuel.
So any other questions?
I think Samuel has unmuted.
I think he is not there, sir.
No, he has unmuted, but his voice is not audible. Yeah, Samuel. Anyway, participants, those who have specific queries, you can just send me an email. So I will be happy to answer the questions.
Sir, good afternoon. Myself, Deficiency from Centurion University. Sir,
Yeah.
actually, PP, sir, you have mentioned that software. Is it open source software?
Which one? Which
PV,
one?
PVSys and PVSol, sir.
No, they are not open source. They are commercial, but you can get trial versions.
Trial version we can download from.
Yeah, for 30 days. but it will have limited features.
Yes, sir. Sir, is there any feasibility where we can learn that software, sir? Actually, we want some training. Is there any training institute?
Yeah, I think there are some persons providing training. Maybe if you can send me a mail, I will share the information of resource persons.
Sir, thank you, sir.
Yeah.
Sir, can you give the mail ID, sir? Actually, the students actually they're doing the domain. We're giving domain projects, so they're very much interested to learn that software. So at first,
Okay. So you can note down simple mail ID for me is yrr.energy.
why
I will share it in the chat, yrr.energy@gmail.com.
sir again, sir, please. Why?
yrr
Yes, I got, sir. I got.
yrr.energy@gmail. If you have any queries, you can send it.
Okay, sir. Thank you.
Any other queries?
So, Professor, thank you. Any other questions?
I think most of
I hope most of them went away.
Yeah.
Yeah, thank you very much, Professor, for delivering a nice session on solar hybrid energy systems for the past 1.5 hours.
I hope.
So this is the second session we attended. Yeah, it was a very nice session, and even your past session was very nice. So we are very happy to have you for this FDP session. So hope we will continue your sessions and other research items in the upcoming days with our institution. Thank you.
Sure.
Thank you very much.
Thank you. Can I leave?